Hello everybody and welcome to another video here at TD channel. Today we are gonna cover, we're gonna do an introduction to RenderMan shading language. RenderMan, as a lot of you might know, is a very popular rendering interface that is used by a lot of major Hollywood studios and a lot of smaller production houses to generate very high quality imaging. So one of the things that makes RenderMan so powerful is the fact that it's very easy to write shaders, and shaders can be very smart and communicate with each other and do a lot of awesome stuff that will allow you to do all kinds of cool effects with just a little bit of technical knowledge. So because of this reason, and also because of the fact that learning how to write shaders, I think will expose you to a lot of the math that is needed for computer graphics, and it will also expose you to a lot of programming used in computer graphics. So it's a really quick way to learn, especially if you are, like I am, a very visual person that learns things a lot better if there's a visual aid or a way to visually represent what you're trying to do with your data. So let's go ahead and try to go over the process of creating our first shader in RenderMan shading language. So first of all, let's look at what is RSL, or RenderMan Shading Language. RSL is a C-like language that's designed specifically for shader development. Shaders are small programs used to define shading characteristics in your scene for a render. What are the different shader types? Most renderers support this kind of shaders. Usually we'll have a surface shader, displacement, light, volume, and imager. There's some other rendering packages that will provide ways. They will provide different shader types, like for example, Mental Ray supports also camera shaders. And then in other packages, like especially when you're dealing with like real-time engines, shaders, uh, they also have different kinds of shaders for real-time engines, and they behave quite differently. But the whole concept behind it is the same. You have a small separate program from the main core application, and this separate program is in charge of shading and appearance modeling. So surface shaders. Surface shaders handle light and object interactions, texturing, and opacity. This is usually what your material is. If you've used any 3D application out there, Maya, Lightwave, whatever, whenever you create a material, that is usually a surface shader. Displacement. In RenderMan, displacement is a special shader type that allows you to modify the position of the shading point before the surface shader is evaluated. So this is a very, very powerful way of adding small details. When you think about, let's say, a big dinosaur, let's go back to the classics, good old Jurassic Park. The dinosaurs, there's no way someone will go in there and model all of the scales on a dinosaur, and you need that detail for it to look correct. Uh, Someone could model it. Nowadays, there's so many programs that could model that detail. But back in the day, there was just no software that could do it. I don't even think that there was a computer that could handle that amount of points because those were very light models. However, you were able to get the detail because PRMan RenderMan all the way back then had support for displacements, and it allowed you to add all these minute details. And if you go back and you look at the original Jurassic Park, there's some shots that are quite close, and you can see just all the wrinkles and all the scales in the animal skins, and it's quite awesome. Light shaders. Well, light shaders provide illumination in the scene. It's no surprise, I guess, for people that have been using CG for a while, that you can actually create your own lights. So if you want a light that has a very specific effect, let's say you want a light that with distance is changing its coloration. You know, when it's really close, it's more blue because the light is hotter, it's closer to the source, and as it fades away, it gets more into the orange tones. You can totally code that and make a special light shader to do that. There's a lot of many different other things that you could do with light shaders, especially once you understand uh, the order in which shaders execute. I remember back in a film long time ago when I was working on, we had these special kinds of light that would allow you to color correct the scene. So, for example, if you had your scene and it was all beautiful lit, and then the director said, hey, you know what, this whole area right here, we'd really like to desaturate it a little bit, but we still want to, it still has to work on 3D. It's not something that you can cheat on 2D. We had specialized that we could just point him at the background and bring the saturation of whatever that light hit, bring it down. And it was extremely useful. And there's throughout the years, people have come up with a lot of many different techniques for lights, not just for illumination. One paper I think was published was in 2006 on SIGGRAPH. It's called "Having Fun with Magic Lights" on a SIGGRAPH course, and it's just a really cool way of thinking how lights could be used other than just for illumination. Volume shaders, when you think about it, the world we live in it has millions and millions of microscopic particles flying everywhere, through our environment. In CG, that is usually not present. You can think of CG as being rendered usually inside a vacuum where there's no participating media. Uh, and sometimes you need that, especially if you're trying to create like a cone of light, God rays or something like that, or dust and smoke. A lot of times the best way to recreate that is with a volume shader. So once again, as RenderMan's job is try to give you the tools to recreate reality and try to create, like all these amazing special effects, it needs to have a way of rendering volumetric media. The imager shader is a special shader type that is run at the end the of the shading pipeline. So basically, the order in which things go is first this displacement, at least in RenderMan. First, the displacements are evaluated. Then the surface is evaluated. The surface is in charge of calling the light. So the surface evaluates the surface light, and then as the surface is evaluating, it will also evaluate internal volumes if you create an internal volume shader, or external volumes as you create an external volume shader. Um, so once again, we have displacement, surface calls light, and volumes. And then at the end, the pixels are ready to be displayed on the screen. And at this point, you have this one last shader that's called the imager shader, and it will allow you to intercept the output. So with an imager shader, you could do something like uh, desaturate everything. Think of it like a post-process on the render. You could desaturate colors, do color shifts. I did one some time ago that would allow you to have like this, that it would have like this old picture effect. So it would look like those pictures from, I don't know, the wild 1800s. It was all faded and scratched and stuff. And you can do that with an imager shader. Now, granted, if you do that with a compositing application or a image application such as Photoshop, you'll be able to do a lot more. But there's sometimes certain effects that you can still do inside the render, and imager shaders could still be very useful. So what are the necessary tools we're going to need for this to write shaders? First, you're going to need a code editor. Personally, I use Vim, but you could use Emacs, Notepad++, Visual Studio, whatever code editor you want. I highly recommend that it's an editor that has syntax highlighting and that it recognizes indentations and just that kind of stuff. That is a full working code editor, not just a text editor. If you try to develop in Notepad or WordPad or something like that, it's going to get really ugly really soon, and it's not going to be enjoyable. Then you're going to need a RenderMan shading language compiler, which usually ships with every RenderMan compliant render, which is the third thing you're going to need, a RenderMan compliant render. So before we get to do any work, we're going to need to download a render. Here's a list of some free RenderMan compliant renders. They're Axis, Pixie, or 3D Light, and you can Google or just search on the internet for these ones. Then you have RenderMan Pro Server, which is Pixar's render. It's quite expensive, so I only recommend you do this if you already have access to this render. If you work at a studio that already has RenderMan, you could follow along this tutorial and use RenderMan. If not, I really recommend you get one of the free ones. We're going to use 3D Light, which is a very, very capable render. And if you go to 3dlight.com, this is the website that you would run into, the 3D Light website. And as you can see on some of these images, it has been used on films. such as Charlotte's Web, District 9, a couple of smaller films that are direct to video or different markets. This is a cinematic for Mortal Kombat, I guess. So it's very capable. So if you go up here in products and you pick 3D Light Studio Pro, it's going to give you a download link down here. So from here you need to select which OS you have. I downloaded this one because I'm running on Macintosh, but any one of these would work. I really recommend that you follow the documentation on how to install 3D Light properly. So, you know, each one of these has their own documentation. So once you download it, go ahead and install it, and then we are gonna get ready to use this. So, hello world surface. Let's go over the process of creating our first surface shader. I think that's this last slide we have. So, as I told you guys, I have downloaded 3D Light. It's installed. One way you can make sure that it's installed, you can do type render DL and then -v. And then that will tell you the version of RenderDL. If you type that and the computer tells you command not found, either it was not installed properly or the application is not in your system path. Just really go back and look at the documentation of how you're supposed to install this software. But this is pretty much what we need. So let me clear this. If you look at the current location I'm in, I'm all the way into a folder called files, and in here, if I list the directory, I have a folder for source, rib, binaries, and a makefile. So without going into much details, I'm just going to go here into source, and then let me see what my hello world looks like. So this looks like a complete shader pretty much. So this is what we're going to be creating. Let me get out of here. And let's do, let me rename this. Right, we're going to call the hello world final, and then we're going to do vim hello world.sl. So this is going to be a brand new file. So the first thing we're going to do is we're going to create the shader. So usually we're going to create a surface shader, and to do this, you're going to type the surface word. That lets the renderer know that you're trying to write a surface shader. Then we're going to put two parentheses. You don't need to put anything between them. Then we're going to open curly brackets, close curly brackets. And in here we're going to type very simply OY equals OS. And then CI equals OI times CS. So what does this mean? These are shader globals. OI is the output of opacity, and you're setting it to OS, which is the input of opacity that you're going to pass to a renderer. And then CI is the output in color. And what we're doing here is we're multiplying the opacity times the surface color. And this is what it's known as a pre-multiplied alpha. I'm sure you guys have used it in different applications or Nuke or something. This is really what it means. First you compute the opacity, and then you multiply the opacity by the alpha to avoid having these fringe effects on the edge of your geometry. So once that is created, we have to give the surface a name. Actually, I forgot here. We're going to call this hello world, and then we're going to save it. So right now we need to compile this shader. I'm going to quit out of my editor, and then to compile a shader in 3D Light, you use a command called shaderdl. And if you call shaderdl with -h, it's going to give you all of these different flags that you can pass to your command. Now, don't get, you know, it might be a little bit easy to get intimidated or flustered by the amount of text that it printed out. But as you start working more and more on the shell and as a technical director, this is usually how a lot of tools work. So you get really used to it. So when I look at this, I see up here that there's a -d, and then it says name afterwards. So that allows you to specify an output directory for the compiled shader. So I'm going to take advantage of this. So I'm going to do just let me go up one level, and I'm going to do shader DL minus D. I'm going to tell it to put it on the bin folder for binaries, and then I'm going to tell it source hello world.sl. If you hit enter, if it didn't complain or it didn't write anything to the screen, that means that it actually compiled. So if I do ls bin, you see that in the library we have a file called hello world.sdl. So this is a compiled shader. If I do cat bin hello world SDL, and cat is something that was just going to print the contents of that file to the screen, you're going to see it's going to be a whole bunch of instructions here. It's not really a binary file, but it is in a format that the virtual machine that handles all the shading can understand it. So that's one of the one of the added features and benefits of using a RenderMan compliant render. I compile this shader in a Macintosh machine, and it will run on Windows or in Linux or whatever other operating system this render is supported on. Other renderers, you would have to compile um, a different shader for a different OS every single time. So now that we have created that, we're going to edit a rib file. And a rib file is a file that will define the scene. So we're going to go into Vim rib, and here we're going to have a file called sphere.rib. So here's a little rib file, and it's very simple. The first line, I'm just going to go through it really quick. The first line tells it the resolution that you want to render is 500 by 500 with a pixel aspect ratio of 1. Next is how many samples per pixel you want to do, the kind of filter you want to use to filter these images, shading rate. This is how fine the detail of your image of your shading calculations will be. We'll probably have another course to really explain a lot of this. Then you're telling it you're beginning frame 1. Then you're going to set a search path option, which basically tells the renderer where can I find shaders, and you're telling it that you're going to find shaders in a folder called bin or at the current location or at the standard location for RenderMan, which is this ampersand sign. Then the display tells it what you want to do. We're going to send it an image called test.tiff to the frame buffer, and it's going to be an RGBA image. Projection is going to be a perspective with a field of view of 40. Then we're going to have a couple of light sources, 3 of them actually, an ambient light, a distant light, and a point light. And these are also shaders right here, by the way. Then here, we're going to set our color to be 1, 1, and 0, 3. So this is R, G, and B. So it's going to be more on the yellowish side, I think, and less with very little blue. And then here we have this surface call. We're telling it that we're going to use the shader hello world. That's the shader we just created. And here we're giving it a whole bunch of different attributes that we don't need. So let's go ahead and copy this line. Let's do, and let's comment this one out. And let's just do hello world to read the shader as is. So we're going to get rid of this. And then here there's a couple of a translate command to move the sphere around, rotate it, and then we finally tell it that we want to create a sphere. Here we do attribute end. So you see between attribute begin and attribute end, that's where we defined our geometry and our shader and everything. Then we do a world end, and then we do a frame end. So that's pretty much all of our rib file. Now what we're going to do is we're going to render the file. But before we do that, let me go ahead and take this option search out, because there's something I want to demonstrate. So if I quit out of here and I do render DL rib sphere and I click render, you're going to see right here, actually let me exit out of this, it's a little too big. I'm going to put this on this side. So this is what it rendered. So it's a little bit yellowy, like I told you, but you can see right here that it's telling us that I cannot find the shader hello world, and instead I will use default surface. Default surface does support the color input, so it's pretty much rendering this way, but as you can see, there's no lighting information here, even though there's 3 lights in the scene. The default surface, what it does is it thinks of your camera as if it was the light. So this is like a matte object that's been illuminated directly from the camera. So how do we get around this, and how do we tell the render where to find the shaders? And I had already gone over that. So if we do vim rib sphere, and that's why I commented this out, because I wanted to show what happens when the renderer can't find the shader. So now we're telling it, for your search paths, for your shaders, I want you to use the folder that's in the current directory /bin. That's the first place you're going to look, and then you're going to look at your default 3D Light location. So we're going to write this, and then we're going to render again. Okay, so there you go. The renderer didn't complain anymore, and now the image went completely solid. Let's look at the source of Hello World. And you can see here the reason it's solid is because we didn't do any lighting calculations. All we did was take the incoming color, the incoming opacity, and multiply them together. So if I go here and I open rib and do sphere, and I tell it that I want to change the color to, well, let's do this 0.5 or 0.2, write that, and then let's try to render this again. We render that again. As you can see, the object changed colors because I changed the value of color. Something else that you could do opacity. So if you do opacity, and I know in a lot of programs opacity is thought of as a float value, but in most high-end renderers is usually considered a color. So if I set this to 0.5, 0.5, and 0.5, half opacity, and render this, you should be able to see a difference between the previous image and this one. Since the background is black, you can't see that it's transparent, but you can see that it's dimming. That means it's becoming transparent. So that's pretty much what we get with this file, right? So this is not too exciting or too cool. So let's try to add a little bit of information. Let's go ahead and go into our shader, and we're gonna add one parameter here. And you see these two parentheses here. Anything that you put in between these two parentheses will become the parameters to the shaders. These are controls that you've given to the shader user, and they can use these controls to change the behavior of the shader. So we're going to type here uniform float KD equals 1. Right? So now we have that, and this is going to be the multiplier for our diffuse coefficient. So in here, what we're going to do is we're going to create some local variables, and we're going to do normal, and n equals normalize n. And the reason we're normalizing is because a lot of shading calculations become cheaper and more efficient if you normalize your normals. Once again, we'll have a course on vectors and normals and all of the vector math. And if you look at that video, this will make a lot more sense. So now that has been normalized, we're going to go down here, and instead of just multiplying the color by the incoming color, we're also going to multiply this by KD times diffuse of n. So right now, just officially added a diffuse term. So if I go here and I tell it to compile, and you can see down here, this is one of the things you can do with a Vim editor. While still in the editor, I can do ampersand, exclamation point, and then just do something like render DL, and then rib sphere, and then you click render. And this didn't update because I was in a different image. Let's look for it. Where is it? Okay, let me coil this really quick because I'm getting confused of which is the one that I just created. Oh, we forgot to compile. So let's go ahead and compile this. Let's do shader DL -d dot bin, and then source hello world. So it compiled, and now we can render again. So there you have it. You can see that now we actually have illumination going on. It's a little bit dark. So how can we change that? Well, if we go over here and we go to the other file, we can go to our ambient light. The intensity is of 0.1. We can increase that. Well, let's increase the intensity of all of our lights. We give that a save. We render again. And now it's getting a little bit lighter. So you can see we have our diffuse term. Now, one of the things we're running into right now is every time I'm trying to build the shader and then render, it's it's two commands you have to type, and it would be really cool to be able to do things faster. For this, what a lot of people use is what's known as some kind of builder or a building platform. There are many out there, such as there's one called Nant, there's Ant, there is Scons, there's Make. Make is one of the oldest one, and it's available on most Unix machines. It's installed usually by default. So we're going to use that so that we don't have to type this every single time. So I'm going to show you guys really quick what a make file looks like. So if I go here and do edit make file, this one's already on disk. This is what it looks like. Basically, I'm creating a rule called all, and that rule is going to depend on a rule called render, right? So if you could see down here, there's a rule called render, and that rule will depend on compile. And even though these are not in order, it doesn't matter. And then when you look at compile, what does compile mean? It means to do shader dl minus d bin source hello world. So basically the command that we were typing for compiling, and then the render is just render dl rib.sphere. So if you create this and you save the file as capital make file and you're in a Windows or a Linux environment, all you have to do at this point, every time you want to re-render, is you can just type make. And by typing make, it's going to run both commands and then it's going to compile. So this will allow us to work a lot quicker. We're going to have another video on building systems, but just, I just wanted you guys to get comfortable with that because I'm going to be using it while I work. So let's go back to our shader and let's try adding a little bit more information to it. Now, one thing that I didn't do is show you how this KD actually works. So as you can see here, hello world will take a parameter called KD, and that is going to be multiplied by the diffuse value. So if I go to the rib file and I go in here and I do float KD, and I'm going to give it a value of 2. So I'm telling it that I want double the amount of diffuse intensity, and I do make again. You see, it got twice as bright. So without me having to go into the original source file, just because the shader developer, in this case myself, gave me this control, I was able to make the sphere look brighter. Likewise, if you do 0.5, you should see it be a lot darker. Okay? So let's set this back to 1. Go back to our file for the shader, and we're going to add a couple of extra things. First, we're going to add a specular term. So we're going to turn this into a plastic, and that's pretty much going to be the end of it. So for now, we're going to go in here and do uniform float ks for specular. I'm going to give it a value of 1. Uniform float roughness, and we're going to give this a value of 15, and then we're going to do color specular color equals color 1. Okay, so we've added 3 new parameters to our shader. The first one is ks, which is our specular coefficient, how strong the specularity is. Roughness is going to control how rough the specularity is, and then specular color is going to control what color the specular highlight is. As you can see here, I am adding RenderMan Shading language supports the float type, and it also supports colors. Since it's a shader and you're going to be doing color calculations, it supports colors. So we're going to go down here and we're going to add a couple of internal variables. we're going to add a vector. We're going to name it V, and we're going to tell it that this is the inverse normalized value of I, capital I. So as I explained earlier, there are some shader globals that are available to every shader. So for example, OS is the input opacity, CS is the input color, OI is the output opacity, output color for CI, and then you also have N, which represents the current shading, the current piece of geometry normal. So the normal for the current piece of geometry is represented by the value N, is of type normal, and then there's a variable called I, which represents the vector that is coming from the camera all the way to the surface that you're shading, to the point that you're shading right now. So think of it as a direct ray or line that is going from the center of the camera to the point that you're shading, and that's usually represented by I. So for this calculation, what we're going to do is we're going to normalize that value, and normalize means that we don't care about how long the ray is, we just really care about the direction. Same thing for the normal. We don't care about how long the normal is. We just care about which way it's pointing. So we're going to normalize the I, which is coming from the camera to the shading point, and we're going to invert it by adding this minus in front. And we're going to use that a little bit later to add the specular component. So what we're going to do is we're going to go down here, and where we did this times here, right? So we did opacity times surface color times KD. And then what I usually like to do is I like to add, well, it's not what I like to do, it's what most shaders do. You have to do this. We're going to add to this the specular term. So you could do this, and then the specular term is going to be ks time a special function in RenderMan is called specular. And then here you're going to do normalized normal, V, and roughness. Right? And that we're going to multiply again by specular color. And then we're going to close our operation. So we can do this like this, just so that it's a little bit easier to see. So we write this. Okay, so this is what our shader looks like now. We have our new parameters. We created a V, which was the invert of the incoming light ray. Here we multiply the opacity by the surface color. We add a diffuse term with this call. And then on top of the diffuse term, we're going to add the specular term with this call, which is the specular scalar by the specular call and by specular color. So if I go ahead, write this, and do a make, you can see we have our little specular term right here. So once again, if we want to change this image, we don't need to go back into the shader. We can just go over here, and I'm going to get rid of this line and enable this one just to see what we did. Here, we changed the roughness, we changed the specularity to 2. I can change this to 3 if I wanted. We changed the specular color to be a little bit more on the red side. The opacity we changed, I'm going to get rid of this, and then we're going to do make again. So there you go, the surface has changed quite a bit. If I go over here and I change the surface again, surface color, to make it a gray, save that, run make again, and there you have it. I'm sorry, I forgot a term here. So now we're going to make it gray. So now the surface is gray and the specular highlight is red. Is this correct? Chances are it's not. Chances are the specular highlight would need to be close to what the color is. But this allows you to do things like let's say you're trying to do a metal, something that is on copper kind of tones. So we're probably going to need to make this more kind of like, let's do a 7 here, let's do a 5 here, and let's do a 1 here. First I need to get the first color for the surface. So let's say that that's going to be the color of our copper. So we're going to copy that same color to our specular term. And if I make this, let me make this a little bit wider because the image is starting to wrap. The text is starting to wrap. Okay, so we're going to copy those values, 0.7, 0.5, 0.1, the same values as up here. But what we're going to do is we're going to add here float KD, and we're going to make it 0.2. We're going to take most of the specular, the diffuse term out. So this is what it looks like right now. It would need a little bit more of a reflection to look more like copper, and chances are this would need to be a little bit tighter. Let's try making it even smaller. So that with a little bit of reflection, and right now because of the background color, it's kind of hard to see, but that would allow you to make a different look. So with this very simple shader that we coded that has only 17 lines of code, we pretty much created a very, very simple plastic. Shaders in production for real films are a lot more complicated, but you can see that it's not extremely difficult. You just have to start getting familiar with the programming and with the math behind shader development. So this pretty much wraps our Hello World shader. I'm going to just go over here and you can see the many different images that we rendered. So like I said, this pretty much wraps our introduction to RenderMan shading language. We're going to have a lot of more courses on how to write shaders. So just stick around, and thank you very much for listening.